Good morning to all. So thank you, Dr. Ashok Kumar, introducing about me and then about my briefing about my work. So once again, I thank Dr. Ashok Kumar. Today, the topic which I am going to discuss here is electrochemical impedance-based thin film and thick film gas sensors. So this is the topic which I am going to discuss today. So in this, the outline of the talk, a little bit about the introduction, this electrochemical impedance and then sensor. So basics about electrochemical impedance and sensor, first I will discuss, and then the experimental section and results. Some of the results what we have obtained or what we have done on this sensor based on the electrochemical impedance. Since this work is more related with the electrochemical impedance, so I will discuss in the basics. So more about the electrochemical impedance, what is the basic principle, how it works, and what is the advantage of these techniques. So basically, the sensors you can not only take the sensor results from the electrochemical impedance, you can characterize this device. Usually, there's a sensors people fabricate, and then they give you the display, something either it's like some kind of signals or some kind of current or this kind of signal it will come. But inside what is happening that you may not be knowing. But using this electrochemical impedance, you can characterize the active sensor layer as well as the device, whole device. That is the advantage of electrochemical impedance spectroscopy. You can say it's electrochemical impedance spectroscopy. So that means it's a very useful tool and powerful tool to characterize the device as well as the components. That's why I have taken this electrochemical impedance part for this talk. Okay, so let's go on to the definition of sensor. As you know, because last 4 or 5 days we are learning this sensor technology. So you might be knowing what is sensor technology. So sensor usually is a device. So in this device, it converts the signal from one energy domain to electrical domains. So you can understand the definition from this picture here. There are various sensors. You can say the color sensor, gas sensor, light sensor. There are so many, position sensor. So these are the sensor devices. It looks very tiny. And behind this, nowadays, due to the technology, they are miniaturizing this sensor in the very smaller size. That is the beauty of this nanotechnology. Okay, so we also have sensors in our body. As a human being, we have sensor. I hope you may be knowing that there are sensor in our body. So I hope you may be knowing that we have 6 sensors. So as you know, our eyes is a light sensor, and then ear is sound sensor, and then nose is like smell sensor, and tongue is taste sensor, and then our skin, of course, skin is pressure sensor and temperature sensor. Okay, so there are eye 1, and then ear is 2, nose is 3, tongue is 4, and then our skin is 5 sensor. What is the 6th sensor? You know, 6th sensor, where it is, and what is the 6th sensor? The 6th one is it is located behind our ear. That is the position sensor. So that behind the ear we have position sensor that tells you either you are standing or you are lying down, or the position will be sensed through behind the sensor which is located in the behind the ear. So we have our body itself. There are 6 sensor, and now peoples are, particularly US people, they are saying there is a 7th sensor, the 7th sense. That means they are moving on to one more sensor by metastable state, or you can say our people rishis are doing this. Okay, so now the simplest, more detail about this simplest example of LDR, light dependent resistance sensor. So here how it operates, basically here this light dependent LDR here. So this is photo resistive materials. So it is it's a sensor. Behind that sensor, there are materials. That is, materials are either semiconductor or ionic conducting material. So if you look at these materials, the properties, what is happening inside, what are the changes happening inside. If you look at this, in the case of light dependent resistance sensor, what will happen? There is a change in the resistance depending upon the light intensity. Okay, so that means if you look at the mechanism behind this, once the light is nothing but photon energy you have. So this photon energy is falling on this material. So then there is a sudden change in the resistance. That means the number of charge carriers are changing. Okay,
Excuse me,
so
sir. Excuse
this
me, sir. Sir,
this this
slide.
will this will
Sir,
be, you
excuse me.
can, yeah,
Excuse me, sir. Slide is not changing. Kindly change the slide.
yeah, now
Slide is visible.
it's changing. Now
Same,
now it's a
same
fourth
slide.
No,
slide.
sir. Actually, you have shared a window. You have to share your entire screen. Just go to present now and share your entire screen.
Slide is not moving.
Yes. Sir, actually, you have shared one window. You need to go to the present now
Okay.
again.
Stop.
Then share your entire screen. So click on present now, then share your entire screen, then click
Yeah,
in between
entire
the windows.
Now entire screen I click.
Yes, now it's changing. Yeah.
Now,
Yes, yes.
okay. So that means this slides you haven't seen before. Definition of sensor. These slides, only first slides you were able to. Okay. So again I repeat this. The definition of sensors as follows: they convert the signal from one energy domain to electrical domain. Here you can see some of the sensors I have shown here: color sensor, gas sensor, and light sensor, so on. So here this sensors looks very tiny, very small. So here one of the sensor, if you move on to this in detail, the light dependent resistance sensor. So here they basically we will be having materials. The materials, either it's a semiconductor or ionic conductor, whatever it is. So these semiconductors or ionic conductor, whatever it is, the materials, the electrical properties are changing when the light is falling on it. Okay, so the light is nothing but photon. So once the photon fall on it, there is a changing the resistance, and this resistance you can monitor. I mean, you can trace it, and then you can convert into useful electrical signals. So that is the output of changing the resistance is driven into the voltage divider, and then we can take it into the output signal. This is the one way, the simple light sensor. This is the way it operates, or this is the way the sensors are behind the sensor materials. So now there are different types of sensor. So like you can list here, that is a temperature sensor, proximity sensor, accelerometer, and IR sensor, pressure sensor, and light sensor, ultrasonic sensor, gas sensors, touch, color, and humidity, and tilt, flow. There are so many sensors. So here basically I will be discussing gas sensor or chemical gas sensors. So more detail will be discussed on the chemical gas sensors. Okay, so now centrally the chemical gas sensor, how it operates. Usually if you look the sensor device, it will be very tiny. You may not be knowing what is the what is happening inside, but if you look at the mechanism, what is happening in the sensor behind, this is chemical gas sensors. So usually we have this sensor layer, that is this is an active layer in the center part, that is a sensor layer, and this is housed in the closed environment. And then this resistance, changing the resistance, or the resistance will be keep monitored by very simple this Ohm's law. Apply the voltage and measure the current. So from this ratio of voltage divided by current, you can calculate the resistance. This is time dependent resistance, you can see here. So if there is no changes on the environment here, for example this chamber, so if there is no changes on the environment, there will be a constant resistance. The resistance will not be changing. So if you introduce, or if there is a analyte gas, the gas which we want to detect, or the harmful gas, suppose if you take any harmful gases, if you have ammonia or nitrogen, hydrogen, some kind of harmful gases. So if you want to detect, so if we introduce that gas, then there will be a change in the resistance. So in the case of semiconductors, so we have N-type and P-type semiconductors. Okay, the beauty of semiconducting oxide materials, so it has a mixed valence state, like here tin oxide SnO2, here you have the mixed valence state, that is 2 plus and 3 plus oxidation state. So these are oxides, semiconducting oxide, once we expose into air, so what will happen, this absorb the oxide oxygens, and then it will be converted on the surface, that is oxide ions. You can see here O minus, it will be converted, and then this will form as a space charge layer. So that means we will be getting resistive layer. So once it is exposed into air, this layer will be there. That means here you have the grain, and then here on the surface we have the oxide layer. That means additional barrier it forms. That is a grain boundary and additional barrier it will form. And this will be stable, particular temperature and particular atmosphere, it will be stable. That's why we have the constant resistance with respect to time. So once we introduce the analyte, suppose hydrogen gas, I introduce this 100 ppm, then this is a N-type semiconductor. So then this resistance goes down. Okay, suddenly the drops, and then it will stabilize. So this change in resistance, this is resistance in air and resistance in gas, presence of gas, and divided by resistance in air. And from this formula we can calculate the percentage of response of this sensor, this material. From that you can vary the concentration, and then we can find out the sensitivity of the sensor. So for sensor, the sensitivity has to be the slope has to be higher value and linear. It should be linear. So in this way, so this is basically this way it is sensor is working. The electrochemical, the chemical gas sensor working in the DC method. That means it's a very simple method. The DC, you apply the DC voltage, measure the DC current, and then from that you calculate the resistance. Okay, so now the changing resistance, and with respect to concentration, you can find out the sensitivity of the sensor. So here what happens, the mechanism, if you look at the mechanism, so this oxide layers is formed around the grains. So once we introduce the hydrogen, so the hydrogen will react with this O2 minus. Hydrogen gas will react with O2 minus, and then it will give you the water in gas and then electrons. So that means the space charge layer, once hydrogen is introduced, the space charge layer will be reduced down. It will become very smaller, and then the number of charge carrier will increase here. The number of charge carrier will increase. That's why the resistance goes down. Okay, so this is the basically it is the mechanism. Basically, this kind of process it's happening on the sensor. Okay, so whatever sensor we have, DC method. The DC method is very simple, fine. So if you look at there are many sensor, after few months or few years, it will dying. The reason is if you the barrier in between the barrier and drift, there is a drift on the measuring the resistance. In case of ionic conductor or mixed conductor as a sensing layer, because if you apply the DC method, the ions are a charge carrier, so this will move to from anode to cathode or positive to negative, negative to positive, and then this will build the permanent interfacial layer. So because of that, it is the sensor is dying after a few months or few years. It is dying. The signals may be false signals we are getting. And another issue is with this simple DC method, we cannot measure the other electrical characteristics like capacitance or dissipation factor or dielectric constant or so on. You cannot measure as a just simply if you want to measure it with the DC method. Or simultaneously you cannot measure the resistance and capacitance so on. So as a simple this DC method, if you want to understand the mechanism or if you want to characterize the sensor layer or the device, it is not possible. And the contribution of here, the surface charge layer, grain boundary and grain, you cannot resolve out. So now we need the alternative tool to characterize this sensor as well as sensor material. So for that, the impedance spectroscopy is one of the useful tool and one of the useful technique. It's a powerful technique. So simply, I will discuss in more detail what's happening in the DC methods. And so in DC methods, if you have, this is the material, this is sensor material or any semiconductor material. So here positive electrode, here negative electrode, that means you are applying DC voltage. And then suppose if you have the ions as a charge carrier, so this will with respect to time, if you look at the ions will move from here to here, and then this current will decay. So that means your baseline will be keep drifting. This baseline, this is the baseline. So this baseline will keep drifting, and when the analyte gas comes, and then this again will drift. And then if time goes on, this baseline keep drifting, and at one point of time, this that means either it will resistance will go down or increase. In the case of here ionic conductor, the resistance keep increasing because of the drift. The resistance will keep increasing. So the current is down. That means the resistance will keep on increasing. So this will the main issue when you have the sensor materials in ionic conductor. So now if you use this impedance spectroscopy, this can be avoided, or this can be sorted out. Not only the device, as well as you can measure the many parameters simultaneously. If you use this impedance spectroscopic technique, you can measure the resistance, that means the impedance. Once we come to the impedance technique, impedance, capacitance and dielectric constant, dissipation factor and so on. There are all these electrical parameters you can measure simultaneously. That is the advantage of this impedance spectroscopy. Okay, so here what is happening? What is impedance spectroscopy? Little bit physics this. When the interaction of electromagnetic radiation with matter, what is happening here? So you can see the electromagnetic radiation is the wide frequency, that is the white light. You have this wide frequency range, the whole spectra. So here, if you look at this very high frequencies, gamma ray, X-ray, UV, visible, IR, microwave, radio waves. Okay, so these are the electromagnetic radiation. So here, when it interacts with matter, that means material. Once it is interacts with material, for example, UV and IR region, there will be absorption and emission. This visible region, absorption, emission. This depending upon your material, it will emit or absorb your light, that is a photon, it will absorb. And depending upon the molecules and depending upon the your atomic arrangements, so there will be a rotational kind of movement. The atoms or molecule movements you can find out if you come into the microwave region. If you still move on this low frequency, what will happen? So there will be a electrical polarization and electrical conduction process will takes place. So this is the only the technique it can covers wide frequency. This you can see it's more than 50 indicates, that is 10 to the power minus 6 to 10 to the power 11 hertz wide frequency range it will cover. So none of the techniques can cover this wide frequency range. That is the advantage of this spectroscopy. Okay, so this here there will be when you change this frequency, and here there is a electrical conduction and electrical polarization process will takes place. So people call this dielectric relaxation spectroscopy, impedance spectroscopy, electrochemical impedance spectroscopy, electrical relaxation spectroscopy, complex conductivity spectroscopy. Different name or different nomenclature they call it. So this different description comes due to the different reasons. Like the reason is, the first one is different classes of materials. If you are working on dielectric material and do the same spectroscopy, apply this wide frequency and then measure this the polarization conduction process, then I say it is a dielectric relaxation spectroscopy. And another one is, if you are a different background of the people, researchers, like material scientists and physicists and chemists, they call it their own. Like chemistry people, they basically call electrochemical, and physicists, they used to they are like to call this relaxation or complex conductivity. They are fond of this too. So this is comes due to the different people's, the researchers' background. Usually it's a background as well as the material. These different names comes, but the mechanism and the principle behind these are similar. There is no changes. All are similar. Okay, so here if you move on to this very wide frequency range, how this can be measured, how it can be done. So up to 10 to the power 6 hertz, up to 10 to the power 6 hertz, so the impedance of the material or impedance spectroscopy can be measured with two electrodes. That's very simple. It's a parallel plates. In between, if you put your materials and apply the frequency. Next slide, I will discuss how we can do it, the things basics about, and little bit about how it can be measured. That I will discuss. So this when you change this frequency in this range with this material, once we stuck here, and then we can measure the impedance. Once you go very high frequency, more than this 10 to the power 6 or 7 hertz, so then wave effect will come into picture. So in this case, you cannot use this simple, this parallel plate or capacitor type of measurement. So we have to make it coaxial waveguide or rectangular waveguide. This kind of things we need to make it. So only drawback of this techniques, up to 10 to the power 6, there is no issue. You can take any material, any samples, and then simply put 2 leads and then measure it. But once you go very high frequency, this like visible region and all, so then the sample has to be made into coaxial or rectangular waveguide shapes you have to make, and then you have to probe it. That is the drawback if you go the very high frequency region. Okay, so this is the typical spectra. If you want to understand these materials, the dielectric or conduction process of the material. So this is the typical. You can see this is almost 1 hertz to 10 to the power 13 hertz. Very high, wide frequency range of this material. This is a silver ionic conducting material. So this is the conductivity spectra. You can see here how it looks. So this kind of wide frequency spectra, you cannot measure anything else. It's just I want to show the advantage of or usefulness of these materials. So from this we can understand the transport mechanism, how its ions are hopping or how it is moving. So this is the low range, the low frequency range, whatever it's a constant, that is the conductivity is constant, there is no changes. Once we increase the frequency, there is keep on increasing. So this is a long range transport, this is a short range transport. That means the ions are moving very long range. That means a DC part, and here it is a AC part. It is a localized motion. So this kind of basic mechanism we can understand, and we can get into the material properties very detailed with this spectroscopy. Okay, so now we'll move on to this more basics about impedance spectroscopy. I discussed this. Now this one is restricted within 10 to the power 6 hertz, from 10 microhertz to 10 to the power 6 hertz. So in this case, this spectroscopy. So the sample is placed like two metal plates, and then AC voltage. AC voltage is applied parallel to the sample, and then AC current is measured. So the AC voltage, that means time varying field is applied and the time varying current is measured. So now the ratio of this voltage, time varying voltage divided by time varying current, we will not call it as a resistance, we will call it as a impedance. So that's why it is called impedance spectroscopy. So you may think why we have to call it a spectroscopy. Once frequency, wherever the spectroscopy, the word spectroscopy, wherever the frequency comes on it, and then the frequency, once it is comes, and once you measure their properties, when you change the frequency, measure any kind of properties, then we call it as a spectroscopy, like IR spectroscopy or UV spectroscopy. The frequency, once frequency comes in, and then we call it as a spectroscopy. So here we are measuring the impedance with respect to changing the frequency. So that's why it's called impedance spectroscopy. So here what's happening? We are applying the time varying field and measuring the time varying current. Okay, so then this time varying current, so it will be deconvoluted into two parts. One, there the current will be, one is in phase current, another one is out of phase current. So now this in phase current, the voltage, whatever we applied voltage, and in phase current, so that is the real part of the conductivity, and the in phase current and the current which is out phase, that is out of phase with respect to the voltage, that is imaginary part of the impedance. So the first one is real part of the impedance, and then another one is imaginary part of the impedance. So the real part will tells about the energy dissipation. That means the resistance. It gives you the resistive property of the material. Here the sample resistive property of the material. And this imaginary part will gives you the energy storage. That means it will gives you about the capacity part of the material. It will gives the capacitance and the energy storage. You can say the energy storage property of the material it will give you. Okay, so from this measured impedance, we can convert this data into admittance. So admittance, it's the inverse of impedance, the complex impedance, and then of course we can convert into capacitance or dielectric constant or permittivity, you can say, and then we can convert this into modulus, that is inverse of dielectric constant, or permittivity is modulus. So you can analyze this material either any one of this in this four representation. You can analyze the material electrical property, because each one have their own advantage. So if your material is conducting material, you can analyze them in the impedance representation. So you may be aware of this pole plot. So impedance, you can analyze the material's impedance or admittance. If your material is dielectric nature of the material, you can analyze them into this the permittivity complex spectroscopy or modulus spectroscopy. In this you can analyze and you can get the information of the material, electrical properties of the material, you can get it. So of course you may be knowing what is happening across the resistor, capacitor, inductance. If you apply the AC voltage, so what will happen? The current and voltage in the resistance, it will be in phase. Current and voltage both are in phase. So here it is E equal to IR. In the case of capacitor, the voltage is lacking current by 90 degree in phase, and then in the inductance it will be voltage leads current by 90 degree. So this, I think you might be knowing this very simple things. So if you want to construct or if you want to understand this material, either it is a semiconductor or ionic conducting material which we are using as a sensing layer or any other applications, we need to understand their electrical properties, or electrical, we can say it is an electrical equivalent circuit, how this resistance, capacitance are inbuilt. That means how the equivalent electrical equivalent circuit of the material. So this one you need to understand so that we can tune the material for our required applications. So some of things how it can be done. For example, if you have the ionic conductor, simple ionic conductor, and then you have the blocking electrode, and then measure the impedance. So this impedance, the simple ionic conductivity here, this part, there is a perfect semicircle, and then there is a straight line. Okay, so this is, we call it as a complex impedance spectra, or this we call it a coal plot, coal impedance plot. So from this plot, we can find out the true resistance, that is the bulk resistance of the material resistance. Perfect material resistance can be estimated from this spectroscopy. That is the advantage of this impedance spectroscopy. Suppose if you have a DC method, of course we can find out from DC method the resistance of the material. But I hope you may be aware that the contact resistance, when the metal and semiconductor, if you are going to touch together, so there will be a space charge layer formation. Okay, so that will create the additional resistance. You have the extra resistance it will introduce. But with this technique, with this impedance technique, you can find out the exact resistance of the bulk resistance of the material. The whatever comes due to the contact, so that will be represented, that will comes as a like this line, this straight line. So that is, we say it is a like capacitor, that is double layer capacitor, or this capacitor in the equivalent circuit. This is the generally we represent the ionic conductor, the equivalent circuit. Here you can say this is the resistance, and this is the bulk resistance and the bulk capacitance of the material. These are connected in parallel, and in addition with that, the series capacitance. This is due to the contacts it will come. So this, by representing the data in the impedance, complex impedance, you will have the semicircle. From the semicircle, you can find out the, of course, the true bulk resistance. And once you know this, this relaxation peak frequency, so from that, of course, we can find out the capacitance as well. The resistance and the capacitance of the bulk material you can estimate. So, but whereas in the DC method, you cannot find out the bulk capacitance simultaneously. This is the advantage of this material. And then if you want to know about what is how the contact resistance or contact the capacitance, how it is, the space charge layer, how it is playing, that if you want to know, then you have to represent this data either in this like admittance or this capacitance or modulus. So here you can see this changing the capacitance with respect to frequency. The low frequency, whatever plateau we are getting, this is the capacitance value due to the double layer. I say it's a double layer, or due to the contacts, whatever capacitance rises. And the high frequency, there will be a plateau, that is due to the bulk capacitance. The modulus, just it will be inverse. So from this we can estimate, we can find the capacitance of bulk as well as your contact. That is the advantage of this system, this measurement. Okay, so this is in, if you go in detail, what is happening in this ionic conductor, the base physics behind this. So here usually the materials, you have the like charge carriers. So there is a barrier. Because of this barrier, the resistive part, the conductive part, it will come due to the coping like this. And because of the applying time varying field, there will be a polarization process that will take place at very high frequency, because here we are probing or we are finding the impedance as a function of frequency. Of course, you have here the polarizability, or you can say the dielectric properties. And high frequency, you will be having this electronic, ionic, and then if you reduce the frequency, you will have the dipolar or interfacial polarization. This all the process you can separate out, or you can quantify with varying the frequency. So this you can do with this material, and you can estimate it. Of course, you can find out the space charge layer or double layer capacitance. This is the directly proportional to your number of charge carriers which is present here. So then that is the perfect, if you have the perfect single crystal. Suppose if I have this perfect single crystal like lithium barium fluoride, this is the perfect single crystal. So here the impedance spectra, this is the impedance spectra of perfect single crystal. So you have the perfect semicircles. Once we change this temperature, the diameter of semicircle is reduces. That means the resistance are decreasing. And the same data, if you represent here in the conductance, it's a constant plateau, and then this will keep increasing. So then from this you can find the resistance, of course, or conductivity you can find. From here also we can find out the resistance and the conductivity, and from this, of course, we can find out the capacitance additionally. So here the estimated capacitance comes around 10 picofarad. So the corresponding equivalent circuit is like the resistance and the capacitance are connected in parallel. And the modulus, if you represent the data in the modulus, we will be having this full width of maxima is 1.14. That means we have the exactly Debye behavior. So Debye is this full width of maxima. If it is 1.14, then it is a Debye behavior. So this material is a very good laser, potential laser material. So when we dope with the divalent here, so this can be used as a lasing material. Of course, this is just later with the application I am telling. So now this is perfect single crystal. We have this kind of electrical equivalent circuit, and we have this kind of electrical properties. Of course, we can understand this in depth, and by doping here, you can tune these properties, everything. Now, the same material, when we convert it into nanocrystal, you can see here this perfect semicircle is changed into depressed semicircle. This is not a perfect semicircle. And same thing here, the conductivity is not constant with respect to frequency. So once we increase the frequency, there is increasing the conductivity. And then if you look at the modulus, double prime of the modulus, here we have the full width of maxima, it is more than 1.14. So that means it's a non-Debye process, it's happening here. And similarly, if you move on to other nanocrystalline material, this is lithium barium fluoride, and here lithium tantalum oxides. So lithium tantalum oxide is one of the useful piezoelectric material. So piezoelectric sensor can be fabricated with this. So it is a quite useful, this sensor material, this piezoelectric material. And then this is glasses, and this is ionic liquids. So here, if you look at all this four system, this is lithium barium fluoride, this lithium tantalum oxide, and this is glasses, this is ionic liquids. If you look at this, all are having similar feature, that the conducting process is similar feature. You have a dispersive behavior. So this comes due to the different additional, this we say it's a constant phase element. The electrical property, that means usually ideal or perfect ionic conductor, you will be having capacitance and resistance in the parallel, but here additionally we have the constant phase element. So because of this constant phase element, if you go in detail, this is, we have random barrier model. So we have here the barriers are very random because it's amorphous. The barriers are very random. So when it is a low frequency, when you apply the low frequency, we have the successful jumping. That means the ions move from here and here. It is a long range. You have the long range. Once the frequency is reduced, that means you are changing the frequency. The field is changing. So here we will having this localized motion. So localized, this will hop here and then come back, hop here, come back. So because of that, this localized motions, and there are so many hoppings takes place, and then this keep increasing with respect to frequency. So that we call it as a sub-diffusive, and this part is a diffusive behavior. So this we can understand further random walk model or finding this mean square displacement, and we can understand this one. It's a little bit physics about this. Okay, so now we have seen the spectra, how does it looks in the perfect ionic conductor, and that means single crystals, and then nanocrystal. Now you come into the microcrystal. So now if you come into the microcrystalline materials, you can see here there are grains on it, and then grain boundary. So here, because of the grain boundary, we have the this one more additional part. This is the bulk one, and this is the grain boundary, and this is the contact. So now we will be having two semicircle and then this line due to the contacts. So from this you can understand this material properties, electrical properties. This another one is anionic conductor YSZ, that is zirconia stabilized yttria stabilized zirconia, you can say this way, YSZ. So this is the oxide ion conductor. This is quite useful for oxide oxygen sensor. They are using this material for oxygen sensor. Okay, so now I move on to a little bit sensor part, little fast because time is now less. I move on to the sensor. So solid electrolyte chemical sensor. As I told, this so electrolytes, ionic conductors are used in the chemical sensor. For example, this oxygen sensor. What we have we have the electrolyte. Usually the sensor is electrolyte, and then one side is the sample. Sample means the analyte which you want to measure, or the liquid or gas, whatever, and then reference. Okay, so when we have this kind of configuration of sensor, and then the response of the sensor is voltage is depending upon the concentration, that is ln of the concentration of analyte with respect to the reference. So if the analyte, that means the sample, if suppose if I want to measure the oxygen, once oxygen comes here, particular concentration, we have the reference, that is standard one. So depending upon that, the voltage will be generated and we can measure the oxygen concentration. Okay, so this is the basically sensor in the solid electrolyte chemical gas sensor. So here this sensor, when we fabricate this sensor, the electrolyte, the properties of electrolyte is very important. That's why in the previous slides I discussed about these transport properties of the electrolytes and how it can be characterized. That's we discussed. So now once we come into this case, the sensor, oxygen sensor, so we have this kind of three-phase boundary. So we have usually this gases, and then this electrode, and then electrolyte. So we have the three-phase contacts, or three-phase boundary we have. So in this case, we need the porous structure. The electrode, we have the electrolyte. Suppose this electrolyte, on the top we have the electrode, so it's the conducting material. And then in the conducting material, electrode should be porous. You have to have the porous structure, so that then the oxygen can penetrate, diffuse it. So in this case, the porous structure, maintaining the porous structure, optimizing this porous structure, it's really challenging. So by using this impedance spectroscopy, you can find out what kind of electrode is better, and which condition of the porous structure is better, that can be understand. For example, here this YSZ materials with respect to different electrode, silver, gold, and platinum. So here you can see this. In the case of gold, the charge transfer resistance is very high, whereas this platinum and silver, the charge transfer is very less. But in the silver, the solubility of oxygen will be very high. So they use it, platinum is more suitable. And now the porosity, depending upon the porosity, again it will change also this contact resistance, other things. So that also can be characterized with this technique. And then it can be developed with the quite useful sensor. That is basically impedance spectroscopy is playing major role to develop this sensor, characterizing the sensor and sensor materials. Now another one is lithium sensor. This is usually lithium sensor is used for fusion reactor, because lead lithium alloy is used as a coolant in the fusion reactor. So the lithium will be used as a fuel, because here you may be aware about the fission. There are two types of reactor, that is fission reactor, fusion reactor. So the fission reactor, that means the like uranium, thorium, big radioactive material, you split, you break them into smaller. When we break that nucleus into smaller, so that will emit a lot of radiation, alpha, beta, gamma, and heat radiation. So that is this radiation is really harmful. And whereas in the fusion reactor, you take very tiny like hydrogen. When you fuse it, so it will convert it into helium. So whereas in the Fission reactor, it will emits the radiation and the half-life is so long, and you have to keep it at spent fuel or uranium thorium after spent. You have to keep it in the safe place, the safety issue and so many issues, radiation effect, so many. But fission reactor, nothing. It will convert into helium, and the half-life of, even though if it is a radioactive helium, the half-life is few minutes or few seconds. The harmfulness is very, very less. But the issue here, this will happen at very high temperature. That is, you need at least 100,000 degrees Celsius. So very, very high temperature we need. So that's why now the peoples are using plasma, and plasma they create and accelerate to obtain this temperature. They accelerate the plasma and then in the confine in the space and collide with the ions, and then they create the high temperature. So that is now on the research level, and then of course this will be successful. And here in that fusion reactor, they are using this lead lithium alloy as a coolant, as well as the lithium as a fuel to produce this tritium, this hydrogen isotope, one of the isotope. And then this hydrogen isotope will be again fused with D2. This D2 is available from seawater, you can extract, and this will produce the helium. So this way this reaction will happen, and then you can get the fusion reactor, and we can get the energy can be produced. Okay, so here the lithium has to be continuously monitored. Whatever they have done previously with the sodium, the beta alumina, so there is a drift, because whatever sensor we have, lithium sensor, at high temperature it will not work. So only this is the very oldest sensor developed and reported in 1988, and even though there is, you can see the drift. So that is not perfectly developed. Still, people are working on it. So we have also developed the material for that, the sensor materials. So lithium, lanthanum, tantalum oxide, this material we have developed, but still it has to be fabricated into sensor. That part has to be done. Okay, so now I move on to the thin film and thick film sensor, how it can be fabricated, how this can be characterized, the real results what we obtain from our laboratory. Okay, so the sensor substrate is alumina. This is the, you can see the size. This is around 2 centimeter length and breadth. This is the sensor substrate, and the back side, rear side, we have the platinum heater. The twisted the platinum heater, and this is the back side, and the front side we have the electrical contacts. So the 2 electrical contacts for sensing, and 2 electrical contacts for giving the current to the platinum heater. Because the sensor material works, the best response you will get at high temperature. Of course, there are now the sensor material or sensor layer even works at low temperature in the sense room temperature as well. Okay, so anyway, this heater, if we have heater, the sensor can be operated at high temperature. So that we have to tune the material and so many things. So we have the inbuilt heater. So this is the inbuilt backside inbuilt heater, and front we have the sensing layer. So this is the real sensor. This is the sensor layer that will be housed into the chamber. This is the sensor chamber. So here this is the sensor that the substrate, and then sensing layer is here, and this is the sensor chamber, and here you have the gas inlet, or here gas inlet. Here this is the gas inlet, and then this is for flushing the air. So the air can be introduced, and then to remove this unlight gas. So this is the setup, and then here we have the source meter to apply the current for this heater, and then here electrometer to measure the resistance or whatever, and then response you can monitor correspondingly here. So this is the basic setup. What we have, and here only thing is, in the case of DC method, we use the electrometer. If you want to go for AC, just you replace this DC with AC impedance, we will be connected here, and then we measure that resistance or capacitance, impedance, everything. So here the material, sensing material will be either it will be made through screen printing or pulsed laser deposition method. So that means screen printing usually it's a thick film, and PLD if we made it the film through PLD, we can get thin film. So here we can see some of the, this is a thick film sensor. So this silver molybdenate oxide, this molybdenate, silver molybdenate. So this material, so we developed for ammonia sensor. Okay, so ammonia, where is the source for ammonia? Because ammonia we are using for food processing and textile and heavy water plant. Heavy water plant also they are using this ammonia. So the threshold limit of ammonia is 25 ppm. So if it goes beyond that, if you are inhaling this ammonia, this will affect our respiratory system. So people are suppose working on this industry and they are using ammonia. If by chance if it is leaked out and more than this 25 ppm, and if they are inhaling more than 25 ppm continuously more than 6 hours or 8 hours, then that's more harmful for their respiratory system. So if aged people, they may die also. Okay, so then we need to monitor continuously this ammonia in the industry. Okay, so for that there are, of course, there are many sensors, many materials or many sensors are developed, and the sensors we can monitor this ammonia by like other technique also, chromatography. There are so many other techniques, but they have their own advantage, disadvantage. Thing is, it may be either costly or it may not be real-time monitoring, or somebody, the operator should be there, take the sample and do the analysis like HPLC. So analysis and interpret the results. But that's another extra work as well as money as well, and then the time as well. But this technique is very simple, very cheap. Whatever the conductance or impedance based method, it's a very simple, very cheap also, and real-time monitoring also can be done. Okay, so here usually this sensor, as I told, this DC method is the drift issue. Another thing is cross sensitivity. This material we made like screen printing way. The material, sensor material is pasted on this here, and then when we measure the resistance with respect to different concentration of ammonia and the different concentration of like hydrogen, LPG, we find out the response value, percentage of response value at particular temperature or particular situation. There will be a cross sensitivity. Suppose if we operate the sensor at this temperature, and here we either if it is either LPG or ammonia, we have the same value. But whereas this temperature, we have the only the ammonia is having higher sensitivity value. Of course, then we can operate or we can keep our sensor at this temperature. And but if suppose the hydrogen it comes out twice this ppm, that means if suppose if it is 100 ppm, then this sensitivity may go up. Then we will get the false signal. We are assuming that it is ammonia, but it may be hydrogen. So to avoid this kind of cross sensitivity or cross signal, if we go for AC technique, that is impedance technique, it is much better, because there we can extract the information of resistance, that means impedance, as well as dielectric constant or capacitance or dissipation factor, anything. That means more than one electrical parameter we can extract it, and then the corresponding their capacitance or whatever for hydrogen or LPG, it will be different. So we can nullify the false signal, and we can say exactly, yes, I have only ammonia or I have only LPG. So that way you can make it out. So here in this material, when we introduce this 25 ppm of ammonia, so there is a DC method, there is a changing the resistance. So resistance drops down, and then when we introduce air, flush air, then resistance comes back to the original position. Here this kind of reaction takes place. That means silver and then MOO2N and MOO2, this kind of materials, products are forming. So that we confirmed what we have done. We have exposed this ammonia and then and then after exposing this ammonia, we freeze it into low temperature, and then we have analyzed the material, surface of this material, and then we find out these are the components are forming on the surface. Okay, so now this DC method, this is the issue. Okay, now whatever I discussed in the AC method, just we removed this electrometer and connected with the AC impedance, and we measured this AC impedance. You see what is happening here. That's the beauty of AC impedance spectroscopy. So this resistance or impedance of the material in air at 350 degrees Celsius, this is black circle line, this is semicircle, and then once we introduce 500 ppm ammonia, that resistance goes down very small. And if you look at this spectroscopic plot, this we call it as a spectroscopic impedance plots. So this is in the presence of air, you have like this with respect to frequency. In the presence of ammonia, you see here that resistance comes down. And if you look at the capacitance or dielectric constant, this is in the presence of air, and in the presence of ammonia, you see here the changing the dielectric constant or capacitance. So that means here in DC only you are monitoring the resistance. Now in the AC impedance spectroscopy, that means you are monitoring more than one electrical parameter. So here there is a change in the capacitance also, you can monitor here very clearly. And then we have create and try to understand this material using this equivalent circuit models, and that gives us the more depth understanding. Here you can see the resistance in the presence of air, and capacitance in the presence of air, and resistance in the presence of ammonia, and capacitance in the presence of ammonia. So that means two parameter you can get it. So here resistance is dropping down and the capacitance is increasing. The resistance is dropping down and the capacitance is increasing in the presence of ammonia. Why the capacitance is increasing? Now why the capacitance is increasing? And here this is little bit mechanism, more detail about the mechanism. Usually this kind of illustration I made it. Here you have the this material, silver molybdate, that is a grind. Once we expose in the ammonia, then we are having this kind of conducting layer. This is silver, and these are highly conducting material. And then this is like particles, nanoparticles, and then this remaining we have the remaining is unreacted. This we will be having, and the excuse me. Unreacted one you will be having, and then this is in the long time scale. If short time scale, we will having like this. So because of this mixed phases, and we can again mixed rule, we can say mixed rule. From that we can calculate this resistance, and then Maxwell-Wagner theory, we can calculate the capacitance. So because of this mixed phases and mixed dielectric constant and resistive layer, these changes are happening. And here we did same thing. We fixed a particular frequency and probe this resistance as well as capacitance. You can see the strong changes on the capacitance as well as resistance also. The reason is here the dielectric constant of ammonia is 16.5. So because of the high dielectric constant, there is a strong changes in the capacitance. Whereas if you go into the hydrogen or LPG, the dielectric constant is very, very less, and the changes on the capacitance you cannot see there. That's why this is more suitable. This material with the AC impedance, you can exactly probe only ammonia. This is a very suitable method and suitable material for ammonia sensor. And next one is Knox Gas Sensor. So NOx is one of the dangerous air pollutant due to its toxicity for the people, animal, and plants, and so on. So this can also generate the acid rain and photochemical smoke. Okay, so this source for this is combustion process, automobiles, and this power plant and fuel processing units. That means the like nuclear industry. So they are using thorium, uranium, thorium. They dissolve with nitric acid. So there is a lot of chances of getting this Knox gas, NO2 or NO. This mixture of two, we call it is a Knox gas. So this has to be monitored. It's, of course, as I said, there are various ways you can monitor these gases, but this method, this semiconductor based impedance based sensor, it's very simple. It's very simple and light and easy handling and real time monitoring, and it is very cheap. Price also very less. The only challenges is here the sensitivity and selectivity and reliability. The sensitivity, selectivity. So for that issue we are going the AC technique. So previously we have seen this ammonia sensor. DC method it senses hydrogen and LPG and ammonia. All it sends, it gives the response. But if you go for AC, and you are, of course, you are measuring resistance as well as capacitance. So if you are looking two parameter, the capacitance for changing the capacitance for ammonia is very high, whereas for other one it is very less. So so that's why it is highly selective. It is highly selective. Okay, the same way we used for Knox. The same way we developed the sensor for Knox, that is indium oxide. We have made indium oxide thin film for Knox gas sensing. So this indium oxide, this sensing layer material fabricated through the PLD, pulsed laser deposition method. So here what we have, this indium oxide material, first we made as into pellet and densify this pellet, and then we put the chamber here. This is the chamber here. This is the chamber target, and then this pulsed laser. So this is KRF, krypton fluoride. That is a laser. That is a pulse wise. It is targeted on the this indium pellet, and then when we hit this pulse laser on it, and then this will create plasma, that is ionize this material, and it will create the bloom. So you have the ions, and then this will be deposited on the substrate. The substrate is heated around this case is 773 Kelvin. So of course this can go up to room temperature to 1000 degrees Celsius. The substrate you can heat very high temperature. So that means the crystal will be grown on in situ. That's why we call it as a in situ pulse laser deposition technique. So this will be done on here. And once we made this the heat on this laser here, pulse laser, and this bloom will be created, and this material will be deposited on the substrate. And this substrate now we can characterize by different techniques like X-ray diffraction and then atomic force microscope, so on. We can characterize the material structure and so on. Make sure whether you have this proper thin film and proper structure and all. You can characterize. So we have done it, and this here you can see the grains and the structure also. Pre-XRD we have done it. Okay, so after that we have done both the DC method and the AC method. And the DC method, of course, we have when we change the concentration, changing the resistance, that means the response value also changing very nicely. It is changing very well. DC method, of course, this film also having cross sensitivity with hydrogen. The same material, if you introduce hydrogen, it is also changing, the resistance are occurring. Okay, so now then we moved on to impedance spectroscopic based method. So here first we characterize the material alone, what is happening on the impedance electrical properties. So we change the temperature in different temperature in the air, so the resistance are reducing. Okay, so this is because as you know, the semiconductor, once you increase the temperature, the number of charge carrier will increase and mobility will increase. So because of that, the resistance will reduce, and then the conductivity will increase. So that we understand there is a extrinsic properties of the material, extrinsic semiconducting properties of the material, that we understand from this. And then what we have done, we fixed a particular temperature, this 325 degrees Celsius, and then we introduce 5 ppm of NOx, and then suddenly that resistance, this is in presence of air and this is in the presence of NOx, then suddenly the resistance is increased like this. So now we analyze this spectra, and here we extracted the resistance and the capacitance. The capacitance is resistance is in the presence of air, it is 0.17 mega ohms, and in the presence of NOx it is 0.5 mega ohms. And similarly the capacitance, there is a change in capacitance also here. Okay, so here that's what happens. The Knox gas, once it goes on the surface of this material, and it also takes the electron, it traps the electrons. So then that means it is indium oxide is a p-type semiconductor. So here the charge carriers are again further it is reduced. N-type semiconductor, again it is further it is increase the space charge layer, and then this resistance is increasing. Okay, and the capacitance from this we can spherical model. So from this spherical model, we can say if you have the grain, and then before absorbing this NO minus, you have some space charge layer. Once we have this NO absorbed here, and then space charge layer will be increased. That means this P minus A will keep increasing. So when B minus A keep increasing, capacitance has to decrease. But in this case, our case, it is increasing. The capacitance is increasing because the dielectric constant of this material is here. It is different because the dielectric constant is higher here. This layer dielectric constant is higher. That's why this capacitance is increasing. That means we can monitor two electrical quantities, changing two electrical quantities here. So then we change the different concentration, and then we found this changing the resistance and changing the capacitance, both gives the linear. That means it is the sensitivity is so very good, and then it is linear because we have to monitor this concentration. The TLV of Knox is 25 ppm. So up to 25 ppm it is linear. We have then done this same thing here, different frequency, same thing. We have a fixed particular frequency, and then with respect to time we monitor, and you can clearly see the changing the resistance, changing the capacitance. So this is this technique is very useful, promising technique, and this material, and this is this material as well as this technique is promising for Knox indium based material. Then we have done LPG gas sensor also based on this material. This zinc cobalt oxide. This also gives very nice sensitivity for LPG. So this material, first we have characterized the materials with the impedance spectroscopy, and it gives from this understanding of from this in various atmosphere the impedance spectroscopy, and from that we estimated the DC conductivity with respect to temperature. At there are two regions we observed. One is section 1 and section 2. This is we call it as Arrhenius plot. So section 1 we have the different activation energy for same material. Section 2 only one activation energy, because in different section 1 we have the different activation energy. As I told previously, this you have the grain, and the grain you have oxide ions. That means absorbed gases forms a space charge layer. The grain, surface of the grain, you have space charge layer. This space charge layer creates the barrier. So depending upon the atmosphere, the space charge layer is changing. But once you go to the higher region, high temperature, it is independent of this the atmosphere. Atmosphere means here we have taken its argon, air, and O2. So that means if this sensor operates either argon atmosphere or air atmosphere, here doesn't matter. You are not going to get any change. But here, if you operate, then there is an influence of the atmosphere. So that to find out that we have done this. So we have at higher temperature, this region it is better either if it is argon atmosphere or air or any atmosphere, there is no changes. So that means here it is extrinsic and here it is intrinsic. Intrinsic is only your material properties it can serve. Then we studied the sensing property at this temperature region here. So here you can see here the changing the resistance. This is a DC method, and we have done AC method also for LPG, but there is a changing in the resistance only. In capacitance there is no changes, because the capacitance of the dielectric constant, or you say it's dipole moment, or you can say this one is dipole moment of LPG. It is nearly less than 1, because it's a mixed gas. For butane it is 0.08, and for propane, butane of course 0, and isobutane it is 0.1. Because of the very smaller value of dipole moment, so there is not change. We are unable to see any changes on the capacitance. But whereas the previous two materials, it's so promising for AC technique. But whereas here we don't see anything in the AC technique, but it gives a proper response even DC as well as AC, that means impedance measurement alone. And then this method, you can use it for biosensing. Just this is for bio aspect. I put few things. The same technique, that is two probe technique, and here also two probe. This is you are measuring the resistance or impedance. Here you are measuring the current, and another one is this is FET phase. Here you measure the potentiometry. So this way you can detect the this biological species. This is a biosensor. That means depending upon the biology materials, here there is a response, and here depending upon the electrochemical reaction, you can measure the current, and then depending upon the analyte, here there will be a FET-based sensor, current flow. So these can be done. This kind of sensor also studied or developed with this AC impedance spectroscopy. Okay, thank you for your kind attention. Now you can, if you have any questions, you can raise.
Yeah, thank you, Dr. Mariappan, for this very informative and very wonderful presentation. Now we have the question session, so we are just taking the questions. So let me first check this. The first question.
10 minutes.
Sorry.
So this question is, I will go back if more questions are there before. So this question is from Dr. TB Rajeshwari. If XC2 characterization is sufficient to confirm phase change after Knox is sensed by the AGMOX sensor, this X-ray characterization sufficient?
Yeah, if X2 characterization is sufficient to confirm the X2 XRD is sufficient to confirm. XRD we have done XPS. X2 XRD can give you, because you have this limitation, because the sensor layer whatever you have. So from this X2 XRD, of course you will get. We have done XRD as well as XPS. Both we have done it. Of course, XRD will give you the main issue, the phase, whatever phase we got. If it is sufficient to detect on the X-ray, then it is fine. But if you are unable to, the quantity is very, very small. Like suppose I said it is silver and MON and MOO2, this kind of different phases. If the quantity is very less, you are unable to detect. So then we have to introduce higher concentration of Knox, so that you can increase the quantity of the silver other formation, then you can able to detect. So that you have to play it. If you are introducing a small amount of Knox and you may not be able to get it, then you have to introduce more concentration of your analyte and make stronger your product. Then X-ray is simply we can detect it. Otherwise, we have to go for still high resolution like XPS, other things to confirm it. Of course, because XPS is much more informative. Even you can find out ppm level from the oxidation state. You can say either you have the silver, either it is the metal or silver is oxide form. That you can confirm also that indirectly that XPS also. Of course, XRD, XPS both you need. Both we have done.
Yeah, so I just thank you, Dr. Mariappan. And at this point, I just want to add this: all the characterization we must, as a scientist, think about the story of the elephants, the 4 blind person looking at the elephant. So once we are using XRD, then is a bulk characterization. Once we are using XPS, again is a surface characterization. So information always is dependent on the characterization technique. And then as X-ray is a very good technique, as Dr. Mariappan told. And then so then we have to see the limitations, as you already know, and many everyone is doing XRD, and I struggled also. This my particular experience. I was doing this magnesium oxide, molybdenum doped magnesium oxide, and there was a formation of MgMO4, and so this was the alpha and beta phase, and then we were not able to detect with the XRD. And XRD was showing same phase for this, and there was no difference in XRD phase. And then one was having so much hygroscopicity. This one was hygroscopic, other was not hygroscopic. So there was certainly these 2 compounds were different, but XRD didn't tell anything. And then we did Raman, and then we found the difference. So we have to always think about the characterization technique there. So yeah, so moving to the next question again. This is from PV Rajeshwari. So
what is the lowest detectable?
What is
I can read. What is the lowest detectable limit of indium oxide sensor towards Knox? The lowest we have done up to 0.5 ppm, and below that we didn't go. I think because the experimental issue was creating this traceable level of Knox, because we have to dilute and then dilute to go to lower concentration. That limit, we have some limitation. We went up to 0.5 ppm to 25 ppm. I could detect lower below that also, but we went up to 0.5 ppm. Now people are working in parts where we have done billion, million also they are working on it. Million, billion, ppm. So PPP also people are working. That's a limitation of our mass flow controller. We have done everything in static mode. That means manually we have to make the gas and introduce through syringe. Nowadays we have a mass flow controller. You can set it the whatever concentration you want to introduce, that can be also done. So nowadays that also available. Then you need a carrier gas and everything. But we want to make it in the real practical situation, in the practical atmosphere. That's why we didn't use any carrier gas, anything. Just a static mode we have gone.
Dr. Mariappan, what is the status of this commercial Knox sensors?
Commercial sensor, they have this Knox sensor, everything, whatever I discussed, they have sensors. But the issue is commercial sensor, of course, the lifetime, and there are many sensors you have to import, that price also higher, and the lifetime also matter. If you develop indigenously, particularly this sensor we have worked on when I was in IG car. They have the American, 5-10 years before, they put a lot of restrictions. They were unable to buy any sensor from abroad because of this Pokhran bomb blast. The DAE people cannot buy anything from outside. So that restriction they put, and then they develop themselves. And also the issue, whatever I told, the cross sensitivity. It is a costly and cross sensitivity. That is a issue. Even the commercial sensor we have, whatever we have.
Yeah, participant, if you have more questions, then you can write. And I will ask my one question, Dr. Mariappan, and this is
Yeah.
not a technical question. This is just means your perspective.
Yeah.
So, like when I go to the market or any customer, means supplier or vendor, or anyone else, then means this make in India. So this like everyone I think want to buy India.
Yeah, make in India now. Because of this current issue, no one wants to China and other products because. Okay.
But what happens? This reliability or standardization, that comes issue. So once I see some product or other person, then they are worried. Means if we buy, even is Indian, means we want to buy, but that comes in the mind. Will it be reliable? So then, if you say German, this is made from Germany, or supplier also say the same thing. This is from Germany, and if this is like that, it kind of means reliability or standardization. We believe that this foreign things they are reliable or standardized, means whatever we buy. So what is the problem in Indian standardization? Why?
Yeah. This our R&D, they are having very good. R&D, and then they believe on the whatever data they are giving, and they stick on it, and they try to develop the reality they want to show, and then they make it a reality. Our people, our case, sometimes they are reliability is easy. Whatever you are saying, reliability sometimes they manipulate because of market or because of the money, and they want to get more money, they want to sell more things, so they sometimes they manipulate. Whereas other people abroad, they don't manipulation is very less, and you can that's why people are trusting made in Germany, or okay, it is a high quality or good quality. So if you come into Indian, they have to make it people has to trust it, and that means they have to show that reliability. They have to show, like last 10 years, what is the output, how the response, so on. If they are impressing the people, then they can also come into the market. Nowadays they are also exporting some of the items. The same way they have to, people has to trust first. That for that they have to show the product reliability. It is a long-term process.
Yeah, I am little bit partially agreeing with this one, because in Germany, if you remember this diesel scandal, so
that's also same thing. Sometimes in this Volkswagen,
many companies they have syndicate of the all car companies. So means this means we are also not worse. Means everyone has the tendency to earn money. But my question to standardization means in general. So like I see some stamp on the product, and I can be confident that this is the reliable. Means that kind of the promise is not still coming. Some standardization company. So when I see the sensor in market, Indian made sensor, for example, there may be a few sensors which may be comparable or even better than the German sensors or other sensors. But it is difficult to notice, to identify which one is better. Because
that is true, because we are not still into that particularly for sensor, and we are not into up to that level, because we are developing only. Still we are not having this developed situation. We are still developing, still working on R&D only.
Okay, so participant, I don't think any more questions, so let's thank Dr. Mariappan then, because so okay, so Dr. Mariappan, we are again very thankful to you for taking this session. And yes, participant will certainly get benefited. There are many backgrounds. There are physics, chemistry, and electronics, even computer science. So everyone, even I think computer science people will also get some idea about the materials, whatever being used in the sensor when they use the sensors, or any artificial intelligence or something. So everyone will get benefit from this. So we are really thankful for this, and then I know that you have the different classes that during the discussion you told, but yes, your presence was important, and this lecture was important. That was the reason I especially requested you. And for participant, Dr. Mariappan is my friend, so he accepted the request because I requested on that behalf. So that's why we could have this lecture here. So today, so thank you, Dr. Mariappan, again, and
thank you. Yeah, thank you, sir. Thank you.